Module 8. Designing an ISPU-based roll pitch demo. In this module, we'll make use of the Intelligent Sensor Processing Unit, or ISPU, embedded inside the ALSM6D-SO16IS. We'll use the STM32Cube IDE to implement the algorithm, which will run on the ISPU. The ISPU will read accelerometer sensor data and calculate the roll and pitch angles. We'll then use Algobuilder to display the calculated roll and pitch angles on the PC screen. The ALSM6D-SO16IS is a system in package featuring a high-performance 3-axis digital accelerometer and 3-axis digital gyroscope. It also embeds an ISPU, or Intelligent Sensor Processing Unit. The ISPU is an ultra-low power, high-performance programmable core with high computational efficiency. It can execute signal processing and AI algorithms on data from the sensors. The ISPU is compatible with most common development tools and can be used to implement both machine learning and deep learning on the device. It is equipped with 32 kilobytes of program RAM and 8 kilobytes of data RAM. It also features a floating point unit supporting addition, subtraction, and multiplication. Let's start by implementing the roll and pitch angle calculations on the ISPU using the STM32Cube IDE. The first thing we will do is copy an ISPU project template from the Xcube ISPU function pack to our project folder. Open Windows File Explorer and navigate to c://mems_studio-workshop/ISM330IS_ALSM6D-SO16IS//template. Select and copy the ISPU folder. Then navigate to c://mems_studio-workshop/module 8 and paste the ISPU folder there. Let's now open the project in STM32Cube IDE. Launch STM32Cube IDE. You may be asked to select a workspace directory. The default directory shown should be OK, or you can specify your own. Then click the Launch button. If this is the first time you open Cube IDE, you may be presented with an Information Center window. This window provides easy access to news and resources for ST products. You can close this window by clicking on the X on the tab. Should you want to view this window in the future, it can be opened again via Help Information Center. To open the STM32Cube project, click on File and then Open Projects from File System. Click on Directory to the right of Import Source and navigate to c://mems_studio-workshop/module 8/ISPU/Eclipse. Then click Select Folder. Make sure the Eclipse folder is selected and click Finish. This will open the ISPU template project. You should see it listed in the Project Explorer window on the left. Let's start by renaming the project. In the Project Explorer window, right-click on ISPU and select Rename. Call the project ISPU-roll-pitch. Then press OK. Let's now expand the project to see the project structure. The Includes folder lists several locations from which include files will be loaded. The ISPU utils folder contains utility files, which you will normally not need to modify. CRT0.s is the low-level startup code containing our interrupt vectors. Global.s contains macro definitions for the project. Boot.ld is the linker script which defines the project's memory layout. Peripherals.h contains useful defines that will be used in our projects. Regmap.h defines the addresses for various ISPU registers used in our project. Let's take a quick look at this file's contents. Double-click on regmap.h to open it. We can see defines for various configuration, flag, and status registers. In this module, we'll be reading data from the accelerometer registers and outputting data via ISPU output registers. The output registers are called ISPU_DOUT. Note that each data out register is 1 byte in size, and they are grouped in pairs. The first two data out registers are ISPU_DOUT00 and ISPU_DOUT00B. There are 32 pairs of data out registers. This information will be useful later on in the project. Now scroll down until you reach the accelerometer and gyroscope registers. These are called ISPU_ARAW for the accelerometer and GRAW for the gyroscope. The name then specifies the axis X, Y, or Z. Our algorithms can use these registers to read accelerometer and gyroscope data from the sensor. Next, expand the source folder. The source folder contains a single main.c file. This is the main source file for the project and is where we will add our code to implement the roll and pitch angle calculations. Double-click main.c to open it in the STM32Cube IDE editor window. As we scroll through the file, we see that the template contains two functions, algo00init and algo00. These are the initialization and worker functions for algorithm 0. The ISPU can run up to 30 algorithms. Each algorithm will be implemented in similarly named functions. For example, algorithm 1 will use functions algo01init and algo01, and so on. As mentioned, the function algo00init is an initialization function for algorithm 0. Initialization code for the algorithm should be added here. Note that this function only runs once, whenever the ISPU is enabled. The function algo00 is where the algorithm is implemented. The ISPU is normally in a sleep state. When new sensor data is available, the ISPU wakes up and this function is called. The function processes the new data, generates any outputs, and then terminates. Once all the algorithms have run, the ISPU enters a sleep state again. Lastly, we have the main function. This function initiates the execution of each algorithm when new sensor data arrives, and then raises an interrupt to the host MCU when all algorithms have completed their execution. You do not normally need to modify anything in the main function. Let's implement the roll and pitch angle calculations. ST provides a number of design tip documents on st.com. One of these explains how to compute tilt measurements from accelerometer data. You can find this document by searching for DT0058 on ST's website. We'll use the information from that document to implement our roll and pitch demo. A copy of the document, as well as source code for the calculations, is provided in the folder c:\/mems_studio-workshop/module8/DT0058. Let's open the source code file, which we will use to implement our roll pitch algorithm on the ISPU. Open Windows File Explorer and navigate to c:\/mems_studio-workshop/module8/DT0058. Right-click on the file dt0058example.c and select Open with Notepad. The first function we see is algo00init, the initialization function for algorithm 0. As we can see, the function is empty, since the algorithm does not require any initialization. Now let's look at the algo00 function. Here we start by declaring some temporary variables. ACC is used for storing the 3 raw accelerometer readings for each axis, x, y, and z. The phi and theta variables are used to store the calculated roll and pitch angles in radians. Finally, the roll and pitch variables store the values converted to degrees. Let's now look at the implementation. The first thing we do is read the raw accelerometer data from the 3 input registers for the accelerometer, ISPU, a raw, x, y, and z. We use the accelerometer data to calculate the roll and pitch angles in radians using the formulae from the design tip document. We then convert the values from radians to degrees and output the values via the ISPU output registers. Note that we output the values as floating point numbers. Since the float type is 4 bytes in size on the ISPU, the roll is output via ISPU registers ISPU DOUT00 through ISPU DOUT01B, and the pitch is output via ISPU DOUT02 through ISPU DOUT03B. The last thing that happens in the algo00 function is setting the interrupt bit for algorithm 0. This indicates that an interrupt should be generated for the host MCU to indicate that algorithm 00 has completed and output data is available. To save time in this workshop, we'll copy the code from this file and paste it into our algorithm 00 function in the ISPU main.c file. First, let's include the required math.h header file. Scroll to the top of the file and copy the line pound include math.h. Return to Cube IDE and paste it in the main.c file. Just below the pound, include stdbool.h line. Next, let's copy the algorithm code. Return to Notepad and select all the code inside the algo00 function, excluding the setting of the interrupt bit since this part is already present in the ISPU template file. Then right-click on the selected code and click Copy. Return to STM32 Cube IDE and paste the code inside the algo00 function, just below the line that reads To do, read, and process sensor data. Right-click on the line and click Paste. We are done with the sample code. Return to Notepad and close it. In our algo00 function, we need to make one small modification to the roll pitch code. We need to account for the different orientation of the ALSM6DSO16IS sensor on the IKS4A1 board with respect to the orientation used in the calculations described in the design tip document. We need to swap the accelerometer X and Y axes. We can do this by simply assigning the accelerometer Y-axis reading to ACC0 and the accelerometer X-axis reading to ACC1. Make the change in the file by replacing ISPU A raw X with ISPU A raw Y for ACC0. Then for ACC1, replace ISPU A raw Y with ISPU A raw X. Now save the file by clicking on the Save icon. We can now build the ISPU project. Click on the Build icon. After a few seconds, you should see a message in the console window saying that the build has completed with no errors and no warnings. Let's use File Explorer to look at the output files resulting from the build process. Open File Explorer and navigate to C:/mems_studio-workshop /module8 /ISPU /eclipse/release. The files we are interested in are ISPU.h and ISPU.ucf. They both contain the program data for the ISPU. The ISPU.h header file can be used to configure the ISPU when you are writing code for the host MCU. The UCF file is a file format used by many of ST's tools to configure the ISPU and other programmable peripherals. We have completed the implementation of our ISPU-based algorithm to calculate roll and pitch angles. For the next part of this module, we will use Algobuilder to design an application which will display the roll and pitch data being calculated by the ISPU. The ISPU block, which we will use in Algobuilder, will use the UCF file to configure the ISPU. It will also require a JSON configuration file to describe the ISPU outputs, but we'll come back to the JSON file shortly. For now, let's copy the ISPU.UCF file to the Algobuilder folder for this module. Right-click on the ISPU.UCF file and select Copy. Navigate to C:/MEMS_Studio-Workshop/module8/Algobuilder. Then right-click on the blank space in the window and click Paste. With the UCF file in place, let's return to the JSON configuration file. Algobuilder requires a JSON file which specifies the outputs of the ISPU so that it can configure the block in our design. In our case, we have two floating point numbers as outputs, one representing the roll angle and the other the pitch angle. Our JSON file will need to specify the name and data type of the outputs. For this module, we have provided you with a pre-configured JSON file specifying the two outputs from the ISPU. Let's copy this file to the Algobuilder folder where we placed the UCF file. Open File Explorer and navigate to C:/MEMS_Studio-Workshop/module8/DT0058. Copy the file named ispu.json and paste it in the folder C:/MEMS_Studio-Workshop/module8/Algobuilder. Note that the UCF file and the JSON file have the same name, only the file name extension differs. This is an Algobuilder requirement. In Algobuilder, we will only configure the name and location of the UCF file. Algobuilder will automatically search for and load the JSON file if it's in the same folder and has the same name as the UCF file. Let's open the JSON file to view the contents. Right-click on the ispu.json file and select Open with Notepad. As you can see, the file is very simple. In it, we specify two outputs, one named roll of type float and the other named pitch, also of type float. The outputs must be listed in the same order they are output in our ISPU C code, since Algobuilder will use this information to associate the block's output pins with the output registers of the ISPU. This part of the project is complete. We can now close Notepad. Also close STM32 IDE. We will work on the Algobuilder part of the module next. Open MEMS Studio if it is not already open. Click on Algobuilder, then click New Design. You'll be presented with the firmware settings window. Let's provide a location for the firmware. Click on Browse to the right of the firmware location box and browse to C:/MEMS_Studio-Workshop/module8/Algobuilder. Then click Select Folder. For toolchain, ensure STM32 IDE is selected. Last, select Nucleo F401RE plus X Nucleo IK S4A1, all SM6DS016IS for the target. Then click OK. As with previous Algobuilder projects, we start with a single sensor hub block on the main design window. Let's now add the ISPU block. In the Library menu, scroll down to Sensor Hub and expand it. Select ISPU and drag and drop it to the right of the sensor hub. Next, connect it to the sensor hub by clicking on the sensor hub output pin and dragging and dropping the connector onto the ISPU block's input. The ISPU block is just an empty block right now. It has no functionality and no outputs. We will add functionality and configure the outputs by providing the ISPU.UCF file to the tool. However, before we can do that, we need to save our Algobuilder design. Click on Save, then navigate to the folder c:/MEMS_studio-workshop /module8 /Algobuilder. Now provide a file name for the design. Let's call it ISPU_roll_pitch. Then click Save. Now that the design has been saved, we can configure the ISPU block. Select the ISPU block in the main design window. In the Properties field, click on Configuration File and then navigate to c:/MEMS_studio-workshop /module8 /Algobuilder. Select the ISPU.UCF file, then click Open. This will assign the ISPU program we created earlier in this module to the ISPU block. Algobuilder will also load the ISPU.json file to configure the block's outputs. The ISPU block should now have 2 output pins. Selecting the block in the main design window will also show the output pin names and data types in the information window. The last step is to display the roll and pitch angles in the MEMS Studio window. In the Library window, scroll up and expand the display category. Drag and drop 2 instances of the angle level block to the right of the ISPU block. Select the top angle level block. In the Properties window, ensure the Preset Values field is set to Custom and the number of values is set to 1. In the Name and the Value 1 name fields, type Roll. Leave the unit name as is. Next, select the bottom angle level block. In the Properties window, ensure the Preset Values field is set to Custom and the number of values is set to 1. In the Name and the Value 1 name fields, type Pitch. Leave the unit name as is. Now we can connect the roll and pitch angle level blocks to the ISPU outputs. Click on the top output pin on the ISPU block. In the description window, it will show whether this pin is the roll or pitch output. Connect it to the corresponding angle level block. Repeat the process for the bottom pin. We are now ready to build the project. First, save the project by clicking on the Save button. Next, let's generate the code. Click on Generate C Code. If you get a pop-up window warning you that the directory has not been initialized, click on Overwrite. After a few seconds, you should get a message confirming code generation is complete. Let's now build the project. Click on Build. The build process may take a few minutes. Please pause this video until your build is finished. You will get a message indicating the build has completed in the console window. We can now flash the firmware to the board. If not already connected, connect the board to the PC using the USB cable. Wait a few seconds, then press the Program Target button. Once programming is complete, you will get a message saying that the download was verified successfully. Now click on Connect. Ensure the communication type is set to serial and that the correct COM port has been selected for your board. Next, click Connect to the board. The Algobuilder evaluation window should appear after you have successfully connected to the board. Press the play button in the top left to start streaming data from the board. You can select the roll and pitch displays to view the roll and pitch angles as you tilt the board. You can also use the custom layout window as we did in Module 6 to display both roll and pitch angle level widgets on the same screen. Click on Custom Layout to open the Custom Layout window. Delete any existing widgets if the window is not empty. Now select 2x2 blocks to display the roll angle level. Repeat the process for the pitch angle. Now when you tilt the board side to side and backward and forward, you can observe both pitch and roll changing. Once you are done testing your application, you can press the stop button. Next, disconnect from the board. Click on Connect and then Disconnect. In this module, we saw how to create an ISPU project using a template from the Xcube ISPU software package. We looked at how we can add our own code to read and process sensor data and output the results. We learned how to build the project and which files to use to program the ISPU. Lastly, we used Algobuilder to quickly develop an application to read the output data from the ISPU and display it in MEMS Studio. This completes Module 8.